We are on page 13 of our notes here, 8.6. We have two examples here, starting with a proof. Okay, the question says, prove the scaling conjectures for the surface area and volume of a rectangular right prism with dimensions length times width times height, and we see the diagram right there. So what we are doing here, we are proving the conjecture. The conjecture means, well, we said that surface area ratios are the scale factor squared. That's what we're proving, okay? So we're going to use algebra to do this. So the surface area of this prism here, or any prism, is given by this formula. What we're going to do now is introduce a scale factor. We could use any letter here. Let's use K. It says let K be the scale factor. So if we are thinking about creating something larger, let's say we just focus on length. If we're going to make this twice as large, that would be our scale factor of 2. This would be 2 times L. This would be 2 times W. This would be 2 times H. So what we're doing is we're multiplying all our lengths and widths and heights by 2. Or in this example, we're using K instead of a number. So we see 2, KL, KW, so on and so on. So the K has just been distributed into all our lengths and widths and our height. If we combine the K's in each of the terms, what we have here is a polynomial with 3 different terms that are divided by addition. We see that every term, well, it has a common 2 in there, but more importantly, what we want to focus on is the K squared. We can pull out the K squared. If we do that, what we have left inside is the surface area of the original. It's just kind of written in a different way. And so what we have in fact done is we've proven that the ratio of the surface area is in fact the scale factor squared. We're supposed to do the same thing with volume. So again, we know the conjecture. The conjecture is that the ratio of volumes is the scale factor cubed. So this one's in fact a little easier because our formula is simply length times width times height. If we have a scale factor of K, we have to multiply that again, same deal, into every one of our length, our width, and our height. So the volume of our new prism would be written out like this. Now what we'd simply do is pull out the K from everything, because if you look at the first line here, we actually have this as K times L times K times W times K times H. So we can simply pull out a K cubed. And what we have now, as you see, K cubed is simply a scale factor cubed, and we have the volume of the original. So we have proven that the ratio of the volume is scale factor cubed. Okay, example 2 here. It says a plane parallel to the base of a cone divides the cone into 2 pieces. So the question, it says find the ratio of the surface area of the small cone to the area of the large cone. So the way the instructions are saying it, they want us to deal with the small cone first and the large cone second. So let's just look at what we know. The height of the small cone is in fact 3 centimeters. The height of the large cone is 3 plus 5, which is 8. You may think that, hey, we need to get out the formula for a cone, and that is one way to solve it, but with what we know about the rules and conjectures in the last little while, let's use what we know about the surface area and scale factor. So remember, if we are talking about surface area, so what we see very first thing, this is the surface area of the small cone to the surface area of the large. When we're talking about how that relates to the scale factor is squared. So all we need to do is put the height of the small one over top of the height of the large one, 3 over 8, and we square that. That works out to be 9 over 64, or 0.14065. Either one is a correct answer. We're asked to do something similar. Here we are asked to find the ratio of the volume of the large cone to the volume of the small cone. So the way it is stated here, the large cone should be written first, then the small cone. So the formula is similar, except we have flipped things around. We have the large cone on the top, the small cone is on the bottom. Now we're dealing with volume. So the scale factor is cubed. So we have 8 over 3 cubed. That equals 512 over 27, or 18.963. What that means is, if we're thinking about how much volume or how much the larger cone can hold, it can hold 18.963 times more stuff than the small cone. And on to page 14 of our notes.